NMOS device which has an N channel consisting of electrons as carriers in the channel, we have a complementary device which is the P channel enhancement mode MOSFET, or you may call it a PMOS. Why? Because the carriers, the mobile carriers in the channel are primarily the holes. Okay, they're not the electrons. So positively charged carriers are there in the channel. You see, your source and drain are p doped, and the substrate is n type as opposed to what you had in NMOS. So this is a PMOS structure. So for a given channel width of W, okay, this W is into the plane of the slide, and then you have the length of the channel given by capital L. These are the geometrical parameters of MOSFET, which are in the order of microns. It's a small device. So if you apply the gate voltage, okay, the gate voltage is such that the plate will accumulate the negative charge, okay, and since this n-type material is consisting of predominantly the free mobile carrier, so you will have the negative charge at the bottom of the substrate of the semiconductor body, okay, and then the minority carriers are attracted towards the bottom of the MOS capacitor, or at the interface of semiconductor. So you have this positive charges accumulation, and they result in a creation of a channel. So you have a channel like this. So this favors, or this forces the current from source to drain. Okay, the direction of the current is as such that you see the polarity of as you can see VSD. VSD is source to drain voltage. The polarity is such that you have a negative terminal at the drain terminal. So the positive is connected with the source. This is your source. This is your drain. Okay, so it is pushing the holes from the source all the way through the channel down to the drain. Okay, if you consider the direction of conventional current flow, well, the conventional current flow direction will be the opposite of the whole carrier's movement. Okay, the whole carrier movement is from source to drain. The conventional current is the other way around. Okay, it's always taken the other way around. Now, how much current is generated from source to drain? It depends on the density of the whole carriers available in the channel. It depends on how much gate voltage is there. Okay. Now, if you increase the magnitude of this VSG, the gate voltage, you see more and more positive mobile carriers. The charge density around this metal and the oxide and the semiconductor interface increases. Therefore, the channel width is increasing. Okay, the channel depletion region is increasing. The channel size is increasing. So you have more and more density. Therefore, you have more and more charge density. So it results in more mobility of the charge carrier. So more current can be more current is expected if you increase VSC. Okay, so this is the IV characteristics are very similar to NMOS. So these characteristics are for NMOS, and you have a very similar characteristic for PMOS. You see, as you keep on increasing VGS, in this case that was the gate voltage. Okay, as VGS is increasing, your the current between source and drain is increasing. Okay, the current is increasing. So because you are increasing the channel width. Okay, you're increasing the channel region, and therefore you're increasing the mobile carriers. So this is the cross section of the PMOS, P channel enhancement mode. Why enhancement mode? Because you need an external supplier to create a channel. There is no channel, okay, without a supply. Without a supply, these two P doped regions are separated by N-type semiconductor. So there can't be any current. Okay, so this has to be, the channel has to be enhanced. The channel has to be enhanced with the external gate voltage VSG. Why we are adding VSG? You see, in if you have noted this in NMOS, we were writing this as the convention was VGS. Why? Because we have VGS. The VGS was always greater than 0. It was a positive voltage source, and the substrate body is kept at ground. But this is a positive voltage. Now, since you are applying a negative voltage over here, then you see VSG is VS minus VG basically the gate voltage is negative. Okay, so to make this whole thing equal to, which is VSG equal to a positive quantity, we write this as VSG. Okay, because your VSG, this thing is less than 0. Okay, this thing is negative. This VG is negative. So okay, the device is cut off for VSG. If you don't have any, gate voltage, of course you don't have any channel, you don't have an inversion layer. So that implies that the device is in cutoff. There is no current from the source to drain. So the dimension W extends into the plane of the page. These are the geometrical parameters that we've discussed before. So W and L, these are fixed from the fabrication processes, and these are small quantities in micron levels. So this is a small device. So the substrate you see now is a N type, okay, as opposed to P type in NMOS. So this is N type, and the source and drain areas are P type. The channel length and width oxide parameters definitions are similar to what we have in NMOS device. Okay. All right. Now one more thing. You see these drain. The convention of this drain we supply is also VSD. Okay, it's not VDS. It's not VDS as we had before. You see in this curves for NMOS we had this VDS. This is for NMOS. This is for NMOS. So because this VDS was positive voltage, you see over here VDS. This is again VDS. This is your NMOS device. So this is again VDS is positive. So VDS was positive, okay, because if you keep on increasing VDS, if you recall from the previous lectures on MOSFETs, this is positive, this is negatively doped. So basically you are increasing, you are reverse biasing this region. Okay, this PN junction is reverse biased. So you keep on increasing, a point come where this VDS reaches to VDS sat, that is the point at which the channel just is pinched off. Okay, is the charge density drops to 0 at the drain terminal. Okay, so we call that as VDS sat, and as a result of that you have a channel like this, you have a tapered channel like this. Okay, and then if you keep on increasing VDS, the ID, the current doesn't change. The current does not change beyond VDS. Okay, so even you are increasing VDS in this direction, the current stays the same. The current stays the same. All right. So yeah, but this VDS was positive. But over here we have, since VD is negative, to keep this quantity as positive, just like before for VSG, we have reversed in notation, VSD, not VDS. Okay, so these are some minor differences to notice. So your substrate is N type. Okay, your drain and source are P doped. Okay, your gate voltage is negative, and we have just changed the conventions of the battery supplies, VSG and VSG instead of VGS and VDS. Otherwise, the operation is quite similar. Okay, you need to have a channel or inversion layer induced from the electric field that is created at the gate and oxide. So in order to have the channel and in order to have the mobility of the charge carriers from source to drain, okay, the operation is very similar, and IV characteristics are all similar. So basically the transistor operation is very similar to what we have in the NMOS. So it's not much difference over here. So what it says is that the operation of P-channel device is the same as that of N-channel device, except the holes is the charge carrier rather than electron. So that's why we call this as PMOS. Okay. In N-channel, in NMOS, we have the electrons which were there in the carrier, which were the carrier in the channel region. So it was NMOS. For PMOS, we have the holes in the channel. A negative bias is required to induce an inversion layer of the holes in the channel region into the oxide. The threshold voltage for the P channel is noted as VTP. You remember last time it was VTN for NMOS. For NMOS, we had this VTN. So just to differentiate, the convention is as such that for PMOS, we had this threshold voltage VTP. So your VSG has to be at least or greater than or equal to VTP for PMOS, just in order to be in order to enable the device or just make the device turn on, the VSG should be at least VTP, so you have a channel for conduction. Okay, since the threshold voltage is defined as the gate voltage required to induce the inversion layer or the channel, Then VTP is also negative. Okay, VTP is also negative. If you're considering this as VG is negative, so you not consider VSG. So VTP is negative. Okay, because the gate voltage over here is negative. Okay, so basically your VG is negative over here. VG is less than 0. If VG is less than 0, then this implies your VTP is also less than 0. The threshold is also less than 0. You have, because you need negative charges on the plate and you need positive at the bottom of this capacitor for the effect to take place. For the effect is to introduce the channel underneath the oxide, okay, for the conduction of current. So once the inversion layer has been created, the p-type source region is the source of the charge carrier, so the holes flow from the source to drain. Okay, over here you can see the orientation of the batteries as such. We have negative drain supply over here, so the p-n junction is again reverse biased. So we have reverse bias junction over here. These are reverse bias junctions. This is reverse bias, but this is forward bias. This is forward bias. Okay, this is forward bias. This battery is going to forward bias the source, so it's going to push the holes from source towards drain. Okay, that's how it is. But if you keep on increasing VD over here, you are increasing the depletion width. Basically over here you're increasing the depletion width, and the point comes when the space charge density at this point becomes 0. Okay, and that's the point where you call this VSD as VSD set. Okay, you have drove the transistor into saturation, then thereafter increasing VSD doesn't make any change in the drain current. Okay, so a negative drain voltage, we have a negative drain voltage, is therefore required to induce an electric field in the channel, forcing the holes from the source to the drain. However, the conventional current direction for the PMOS transistor is into the source and out of the drain. So the conventional current direction and the voltage polarity for PMOS device are reversed comparing to the NMOS device. Okay, so compared to NMOS, the conventional current direction is reversed because the hole carriers are positive over here. So it's the other way around. So note that in figure 11, this is your figure 11, the reversal of the voltage subscript VSG, it hasn't made a positive quantity. The gate voltage is negative with respect to that of source. Similarly, VSD is also positive, okay, because VD is negative. The drain voltage is negative with respect to that of source. So this is also a positive quantity. So the notations are changed as we have discussed this. Okay, we've talked this. So you don't have VDS, you don't have VGS, you have VSD and you have VSG. Okay, and you have a negative terminal at the gate, a negative drain at the, you have negative supply of VSD at the drain terminal. So the ideal MOSFET and current characteristics are very similar to NMOS device. So for the P-channel enhancement mode, essentially the same as that of NMOS. And then it says that there is a point that it comes at the VSD saturation, which is VSG plus VTP. So a point comes when the difference of VSD minus VSG is VTP. And at this point, you call this VSD as a pinch of voltage. Okay, so you call this as a pinch of voltage. This is the point at which the charge density at the drain terminal is 0. Okay, it's pinched off. So there are no increasing VSD beyond this point doesn't help in increasing the current. Okay, so it's just the electric field, establishment of electric field, which is driving the holes from the source to drain, and thereafter increasing at the point after increasing VSD, after beyond VSD sat, we can't increase ID. Okay, so for the P-channel device bias in non-sat region, which is the triode region, the current is given as, so this is the linear region in which you can use this as an amplifier. Similarly, in saturation region, they were very similar expression that we had earlier for NMOS devices. And if you recall, for these expression, you have a conduction parameter Kp over here. This is very similar to what we have earlier for Kn. Now, if you have the this Kp is also defined in terms of the MOSFET width, geometrical parameter, and the length, and then the hole mobility and the device oxide capacitance per unit area. And if you want to increase this drain current in these non-sat and saturation regions, you can have Kp. You can have more Kp if you are going to select the ratio, if you're going to increase the ratio of width to the length of the device. Okay, so this Kp has a pronounced effect on the drain current. Okay, which is the holes, which is due to the holes in the channel from source to drain. So this Kp and the drain current this exists, and this the drain current exists the drain terminal. Okay. The parameter Kp is the conduction parameter for the p-channel device, and it's given by the in terms of geometrical and electrical parameters of the device. So this affects the current. Basically, this affects the current in both the regions, non-sat and saturation regions, where WL, CUX are the channel width, length, oxide capacitance per unit area, as previously defined for NMOS. The parameter mu p is the mobility of holes in the hole inversion layer. Note that the hole inversion layer mobility due to the positive charge holes is less than the electron inversion layer mobility. Okay, possibly electron they have smaller mass as compared to the hole, so less force is required to mobilize electrons as compared to the holes. Okay, so holes are electron deficient atoms, so these are heavier charge carriers. Um, so we can write Kp as this Kp prime is your this is your electrical. This consists of electrical parameters, the hole carrier mobility and the oxide capacitance. So basically these two expressions are the same. Okay, and for a p-channel MOSFET which is biased in the saturation region, you need to have VST which is greater than VST sat. Okay, which otherwise of course it is equal to VSG plus VTP, which is a threshold, because this is the point at which the channel is pinched off. Okay, this is the point at which the channel is just pinched off. So for example, if you have this device like this, and you have those two doped regions, so here you're going to induce a channel. So you have two regions, then there is an oxide. Okay, oxide, and then there is a metal over it. This metal could be aluminum or whatever, so this is your metal. Okay, and then for this n-type substrate, um, which has majority of electron carriers, there will be some holes if you're going to connect a negative supply over here. Okay, that's your gate Vg, which is negative, so you have negative charges over here, and the positive if this is connected to the um, if your source and if your drain, which are p-type, which are both p-type, this is p, both are connected to the ground like this. Both are grounded over here. Okay, so what happens is that you have an accumulation of minority ions or hole carriers, okay, which are electron deficient. So they come over here, and the channel is induced. Okay, so you have a channel over here. But if you reach a point, you keep on increasing this VD, VSD. So VD basically is also negative. Okay, so you have a negative terminal of the battery over here. That's your VD. If I just put this as VD, so you're increasing this region. You're reverse biasing the region. Okay, and this reverse biasing goes on pinching off this channel. So at this point, the channel is looking like this. Okay, the channel looks like this. So once there is no space charge carrier left at the drain side, then increasing VD won't help. Okay, because you have increased the depletion bit so much that it has pinched off the channel over here at the drain side, and thereafter increasing VD doesn't help in increasing the current from source to drain. Okay, so you have reached the saturation. So this VST is greater than VST sat is VSG plus VTP. VTP is the minimum voltage required by the gate to establish the field to have the inversion there. Okay, so once this is reached, this point is reached, we have driven the PMOS into saturation region. Okay, so saturation means that you have already pinched off your channel. You have already reduced them, and order you have reduced the majority carriers in the channel at the drain side. Okay, and the channel is now physically tapered off. It's physically tapered off. It's like this, like this. Okay, so that's saturation. So current is not increasing. It's not dependent on VDS, VST now. That's all.